to follow through and see what we have done for the day, so that they can also go through the same lecture that we have. But I would like to encourage people to be joining, because it is equally important for the interactive objective, so that you can ask questions, you can seek for explanations and all of that. Even having all the members present, it makes more sense. So without wasting any time, let us look at the goals of our today's meeting, which will be to understand now, after knowing what are the operating system, what is the importance of an operating system, what it does, and what it requires for it to function. Now we go into the hardware components and the concepts which are surrounding the operating system and its functioning. So in order to accomplish that, we will be looking at the components of an operating system, just to understand in our computer systems, what are the components that you require so that the operating system can work. Like we had said, it is an intermediary between the application programs and the user, as well as it sits between the application programs and the user and the hardware. So we need to understand what are these hardware components which are usually required for the operating system to function as expected. Then after that, we will try to understand registers, which are also components found in the operating system for it to work. We will also try to understand the instruction cycle as well as instruction registers. We will also try to understand how the program is normally executed, or when you have installed a program in a computer system, how is it normally executed, and where does the operating system come in. After that, we will try to understand the concept of DMA, or direct memory access. We will also try to understand the concept of an interrupt and multiprogramming, as well as the memory hierarchy. For the computer to work, there is always the processor, which is very important, the memory, which can be divided into the long-term memory as well as the short-term memory. So it is important to see this memory hierarchy, the way it is normally organized. So all of that will be very important for us. So for today's class, that is what we are going to try and accomplish. And I hope by the end of the class, you will have accomplished that. So let us try to understand what is meant by an operating system, or during the operation of an operating system. How does it normally work? Now, an operating system will always try to exploit the hardware resources. Like we had said, one of its functions is to be an intermediary between the hardware and the software. So it tries to exploit the hardware resources so that they can be used by application programs, and application programs at that time, they are serving the needs of the user. So one of its activities is to exploit the hardware resources. Another activity is to provide a set of services to the system user. So like what we are calling abstraction, or what we are calling arbitration, that is a service that is going to be provided to the system user. Then it will also be managing secondary memory as well as the input and output devices. So when we are talking about secondary memory, we are talking about this memory which can be attached and removed from the computer system. Think of the external hard drive, the hard disk, which is normally attached to the computer, and think of the other drives. Yes, Mureidi and Rukia. Yes, what can I do for you? Any question? I had seen that you had raised your hand. Okay, maybe it was a mistake. So I hope I'm audible and everybody can hear me. So can everybody hear me? You can type on the chat section so that I know if we are together. Are we together? Okay. Thank you, Muredi. Okay, let us continue. What I was saying, when we are talking about exploiting and when we talk about exploitation, is basically to make use of. So the operating system will be trying to make use of the hardware resources so that it can provide services to the user. So that is basically what we are saying. So the basic elements which will be exploited, we are looking at them now. These will include the processor, which is the main component found in a computer system. It will also exploit the main memory, which we refer to as the real memory or the primary memory. And at this point, it is good to note that this main memory is usually referred to as primary because it is volatile. When we talk about volatile, it means that this memory can lose its content. Whenever there is, when power is switched off or power goes, whatever was contained in that memory would be lost if it had not been saved in the secondary memory or what we refer to as the permanent memory. Then we also have the input-output modules, and these are the components which support the input-output devices like the keyboard, the mouse, the external hard disks, um, audio components like the speaker, the microphone. All of those are what we are calling the input-output components, and they are usually, even the network interface cards, they are usually supported by the input-output modules, and we will see how they normally function. Then we have the system bus. When we are talking about the system bus, these are the small wires which are running. When you open the computer CPU, you'll find so many wires and a main board or the motherboard which connects all of them. It is the reason why it is called a motherboard. It is the mother connecting all the other wires from one component to the other. So they are able to connect maybe the hard drives to the processor to the processor to the main memory and all of that. So those are the wires which enable communication among processors, the memory, and input-output modules. And we are saying all of those are normally tied up to the motherboard or to the main board. Then we continue. When we are looking at the top level components, we normally start with the CPU. And inside the CPU or the central processing unit, there are other small components which are found there. And they are very important for the operating system to work. That is why we are looking at them. These components will include the program counter. They will also include the MAR, which we normally refer to as memory address register, the MBR, which is also called the memory buffer register. We also have the IR, which is called the instruction register. And we also have the input output address register, as well as the input output buffer register. So those are the components which are normally found in the CPU. Somebody says they can't see the diagram. Why? Is everybody having the same challenge of seeing the diagram? or it is your device which is taking some time to load, because that normally happens from time to time. So these components which are found in the CPU, they are also connected at the top. They are also connected to the main memory, and this main memory is supposed to ensure that whatever is being processed can be held by the computer system, or can be held there before it is either output to the user or it is stored permanently in secondary storage. Also, the CPU is normally connected to the input-output module, which enables the input and output devices, either the display, either the keyboard, or the sound producer, that is the speaker, to be able to give an output, as well as the inputs to be captured using these input devices. So this is a top-level picture of how these components will be connected so that the computer system can be complete. Now let us move on to understand, when we are talking about the processor registers, what exactly do we mean when we talk of a register? Okay, let me increase my volume. Is it better now? Grace, are you able
Yes,
to?
it is better.
Okay, thank you. I think it was the microphone which had a problem. So when we are looking at the processor registers, what exactly are they? When we talk of a register, it is a location or a storage location which is quickly accessible by the processor. When you go to the computer system or to the CPU, the processor of the computer, it is actually very fast. We normally talk of the process of the speed as maybe 2.4 gigahertz. What does that term mean when we talk of a gigahertz? It means that this processor is able to either transform, because when the requests land to the processor, they land there in the language of zeros and ones. That is what we said last week, that it is the operating system. When you click on something or when you are typing, this keyboard will send signals to the operating system. These signals will be translated to the language of the hardware, which is the language of zeros and ones. So the operating system will translate them and take them to the processor. When they get to the processor is able now to work on those zeros and ones so that you can be able to see whatever you are typing on the screen. Because when it works on them, maybe a signal is saying type a K. A K could be represented as a 1. Type maybe a I, it is represented as a 0. So that will be interpreted by the processor. And when we are talking about now the processor having maybe 2.5 gigahertz, first of all, we need to understand what is a hertz. A hertz is a measurement of, it is a measurement unit which is supposed to show a cycle. And when we talk of a cycle, it means that the processor is able to move one revolution 360 degrees, and that one revolution is supposed to translate either a 0 to a 1 or a 1 to a 0. That is what we basically mean by a cycle or a revolution. So if it is able to translate a 0 or a 1 in one revolution, which we are calling a hertz. When we are talking of a gigahertz, it means that it is a million cycles, because giga will stand for a million. How do we get to a million? Normally start with the measurements of units, where just to show you, where we start with maybe a hertz. So it is written like that. That refers to one revolution, or what we are calling a cycle, that is 360 degrees. Now, when we are talking about a kilohertz, it refers to 1,000 hertz. Now, when we are talking about a megahertz, it refers to maybe 1,000 kilohertz, whereby we have another 3 zeros. So actually a megahertz is the one which is a million. Then when we talk of a giga, we are talking of how many? To the power of 9. 1 to the power of 1, 2, 3, 1, 2, 3, 1, 2, 3. So that one cycle is normally is per second. So if it can work, if for example, e.g., if for example, we are talking of 2.3 gigahertz, that is a processor working at that speed. It means that it is able to process. It is able to process 2.3, and here we are talking about billion bits of data in a second. So that is the kind of speed we are talking about in terms of a gigahertz. So that is how fast that processor is going to be. So if you are talking about 16 kilobits, those ones can be processed very quickly by the processor, and it is done with that. So one attribute of the processor we will see is that it works sequentially, meaning that it is one request after the other. But to the human eye, we normally see it as working simultaneously, meaning that it is doing several things at once. That is not true. It is always working sequentially, and these requests or these jobs are normally lined up in a list or in a schedule, whereby after one has been served, then it serves the next request. That is why it becomes very fast. Now, when we are talking about the processor register, we are calling it that storage found just next to the processor. Because of that kind of speed and because of the concept of multiprogramming, which we shall see as we move on, the processor is very fast. And if you said that it does one job, then waits for you to save that work for it to work on the next job, then you are wasting resources. So in order not to waste the resources, the processor will transfer whatever it has processed. It will be transferred to the processor register. And these processor registers, like we have seen, they are of several types. So you can talk about these what we are calling the instruction register, which is supposed to store all the instructions which are given to the processor so that it can execute data. We are talking of memory buffer register, which is supposed to store data which has already been processed and it is waiting to be stored elsewhere. Memory data register or memory address register, which is supposed to store information, or it is supposed to store the locations of different sources of data which needs to be worked on. So there are several types of registers which are found close to the processor, which are normally used to ensure that data is stored there and the processor keeps on working and no time is wasted at the processor. So I hope I have explained what a register is. But then we also have several types of registers. And here they are, we are talking about. We have what we call the user visible registers, And these are registers which enable the programmer to minimize main memory references by optimizing the register use. What do we mean? It ensures that if you are the user, you don't need to keep on referring to the main memory, which is the RAM, and trying to have exchanges between the main memory and the processor, but rather you are using these registers so that the processor can access whatever data it requires quickly, or whatever information it requires, be it an instruction, be it the data, or an address location. Then we also have control and status registers, which are used by the processor to control the operating of the processor. Like we have said, now we have those which we are calling the instruction registers and memory buffer registers. These ones are normally used by the operating system so that it can control the routines which are taking place during the execution of programs. Sometimes a program may require some input-output device so that it continues to work. And as it requires that, like we will see the instruction cycle, whatever data it was being processed on behalf of that program will be removed from the processor, put on a waiting list in a register somewhere as it waits for the input-output device to respond to the request and to provide whatever is required for. And during that time, the operating system can schedule another process to get into the processor and be executed. So we have those two kinds of registers, where we are talking about user visible registers, which are normally accessible to the user. And we also have the control and status registers, which are normally accessed by the processor and by the operating system to enable the control of the processor operation. Then let us move on to the user visible registers, and these ones are normally referenced by machine languages. So when we are talking about machine languages, we are talking about the compilers, and basically it is the compilers which are normally used by programming languages, so that these compilers are able to translate instructions which you have given in the normal language when you are programming. And once they have been translated, then the operating system is able to work on them by working on the registers. So they are available to all the programs, especially application programs and system programs. And they are of these types. One is what we call the data registers and address registers, whereby address registers are going to be talking about index addresses, segment pointers, and stack pointers. When you are looking at a program, you can be able to understand what is a stack, and then you are pointing at it. So index registers are going to involve adding an index to a base value to get an address. A segment pointer is used when memory is divided into several segments, and this memory is referenced by a segment and an offset. Now, when we are talking about a stack pointer, it points to the top of that stack when you are looking at lists and linked lists. Then we come to the control and status register, and these include things like the program counter, whereby the program counter contains the address of an instruction which is going to be fetched. So during the execution of a program or the execution of any instruction by the computer system, there is always what is inside the processor, and the program counter will be a register which is storing the instruction of what needs to be executed next. So that is what we mean by a program counter. It stores the address of the next instruction so that the processor doesn't waste a lot of time, but it will just get the address from that program counter. So that is why we normally have a scheduler within the operating system so that it can schedule and show what needs to be executed next. So the processor will not waste a lot of time trying to get whatever needs to be fetched from either secondary storage or primary storage, but it will get it from the program counter. Then we have the instruction register, which contains the instruction which was most recently fetched. So the program counter will store what needs to be fetched next. The instruction register will store what was recently fetched. Then we have the program status word, and the program status word contains instructions or condition codes which are normally available to the operating system to know what needs to be done. Yes, Grace? You have a question? I have seen your hand up. You have a question? Okay, so the program status word, okay. Oh, I am a bit fast. Okay, I will slow down. So let me go back to the program counter and start over there. We are saying all these registers we are talking about, they are basically storages, like quick storages, which can be accessed quickly by the processor. So when we will be looking at the memory hierarchy, you will notice that registers are the ones close to the processor. Let me see if I have that diagram. If I do not have it, I will be able to provide it to you. So I think we have it here. When we are looking at the memory hierarchy, is this diagram visible? I just wanted to explain the concept of registers, and I'm using this diagram. Does everybody see it? Muredi, are you able to see the diagram? And Rukia?
Yes, I'm able to see the diagram.
Okay, thank you.
Yes.
Okay, so when you are looking at this diagram, we normally start with the magnetic tapes. Those are like the old school video cassettes and radio cassettes. Those magnetic tapes were used to store data. Then we also have the optical discs, which are, we are still using them, the CDs and DVDs. Then we have the hard disk, like we know it. And then we have the SSD, or the flash drives. Then we have the main memory, which is the RAM. And then here we have cache memory. We will look at the concept of cache memory, which is also a temporary storage for quick access. And then we have registers as we get closest to the processor. So at the top here, we can have the computer processor, and next to it is the registers we are looking at. So instead of the processor, because as we go up the hierarchy, you will notice that the access is very quick, and also the speed is high to access these storages. But as we come downwards, these are slow storages. As we come down like this, the storages become slow to access, slow to store data, but they are more permanent. The cost becomes cheaper. As we go up like this, they become more expensive. That is why you can buy a RAM drive of like 8 GB for maybe 6,000, but at the same time you can buy a flash drive of maybe 32 GB for less than 4,000, because as you come down like this, they become cheaper, but as you go up like this, they become more expensive. So these registers are quickly accessible by the processor, and that is why they are stored next to the processor. The registers, we are saying, they are supposed to hold information regarding the storage, regarding the instruction, regarding the data to be processed. So all the registers we will be looking at, they will be storing information regarding what needs to be processed, what has been processed, the location of what needs to be processed, and the location of what needs to be stored somewhere. So they surround those three things. Now, the registers are going to ensure that you can access data quickly, you can access instructions quickly, and store them quickly so that the processor can do other things. So I hope up to there I have made sense before I go back to explaining the registers again. Up to there I have made sense. Yes? Okay. So let me now come to these registers. We had said that we have what we call the user visible registers. And we started, the first one was the index. When we are looking at address registers, which when we are talking about user visible registers, are those which can be managed or are those which can be affected by programmers. And programmers will usually work with program development applications. Like if you are talking of C programming or Java programming, it will either have that programming language will have registers and those registers will contain information about the program and
Hello.
Nini inaendelea huku? Mbona hakuna Alex?
Manze pia mimi ndio nashinda sijui kwani kumeendaje.
Inatufinya huku bana, hadi communication pia inakuja ni kama hii. Wacha mchezo.
Haitaki. Sio tena naye.
Unajua kwa moment nilikuwa nadhani ni mimi ndio network yangu ni mbaya bana. Na nikawa na stream from Scott.
Pigieni lecture simu.
Mimi sina credit, atarudi tu.
Ama tumalize hii class. Sisi wenyewe tuimalize.
Anatuharibia
Shida.
data.
Hii bana, hii class iishe. Otherwise mimi sikuwa nimejipanga na hii class yake.
Harakisha tuende tukafanye kazi.
Amedai nisitume potea kwake.
Adolf, wewe huku kumaliza ile kazi nilikupea.
Nilifanya cheki huyu msee.
Ingia WhatsApp saa hizi wewe tufanye kazi kwanza.
Tulia kwanza tusome bana, masomo muhimu.
Akirejea tunajua.
Ati?
Akirejea tunajua amekuja.
Hata ndio amerudi. Hello?
I'm back. Sorry, I had lost power. And the internet got disconnected.
Okay,
so
no problem.
let me reconnect again and share.
Nini na guruma hivyo?
Hata pia mimi ndio nashindwa bana. Sasa tusome sasa Morio.
Okay. So we were looking at the user visible registers, and as I was explaining, we normally have the address registers. Kindly mute your mic so that we don't have an echo. Somebody has their mic on. Mogi Fred. Yes, thank you. So we were looking at the add index registers. I was explaining that user visible registers are those registers which can be accessed or can be made use of by programmers through the program development applications like C, Java, whichever programming language you have, because they are going to have compilers. And these compilers are the one which are going to be showing the processor or showing the operating system what needs to be done. So one of which we have is the index register, and it involves, or when an index register is being used, it involves adding an index to a base value to get an address. Because usually whatever is being accessed or whatever is being worked on is stored in an address somewhere, in a storage location somewhere. So it is the work of this register to be able to get to that address or to store the address of that location to the data which is being worked on by the program. So the index register is supposed to add an index, or is supposed to give if you can talk, an index will be like a label, so that when the processor sees this label, can be able to tell which address that is. Why? Because the address location or the address could be a huge value. It could be a long value which cannot be stored anywhere else. So the label will be used when that address location will be given a label, and it is that label we are calling the index, which will be stored in an index register. So that is what it means. Then we have a segment pointer, whereby the segment pointer, the memory where this data is being stored, especially main memory. Main memory, or the RAM, is where data being worked on by the processor or by the application program is normally stored. So that main memory will be divided into segments, and these segments are going to be referenced to. since their locations are also huge, what you normally do is to put a reference pointer. That is why we are talking about the segment pointer. So you are going to point into that segment of the memory and put an offset so that whenever you want to refer to it, you go to the segment pointer instead of going to the actual location, but you are using the segment pointer, which is a register storing the location which you want to go to as the processor, so that it reduces the time to go to the actual location, but you are going to it through the register. Then we have the stack pointer, and the stack pointer, when you are looking at lists which are accessed by the processor, then you need to know where to begin that list. That is why it is a stack pointer is supposed to point to the top of the stack, so that when the processor begins to access that list, it can be able to know where to access from first. So I hope that one is clear and understood before I go to the control and status registers. Are we okay there?
Yeah, we are okay.
Okay, thank you. Now, when we come to the control and status registers, we are talking of a program counter, which I had said it is a storage or it is a register which is going to store the next instruction to be fetched by the processor. Because the way the processor works, it will be having the data and the instruction which is telling it what to do to the data. Like for example, when you click open, you are trying to open a file location somewhere. You are giving instructions to the processor to go to a particular location to retrieve that file. So it is the program counter which will store the next instruction. Maybe you are talking about now typing the text file. So it is the program counter which will store that next instruction. At the same time, once an instruction has been used, it is the instruction register which stores that instruction. That is why we are saying it contains the instruction which was most recently fetched. So like when you had clicked file open, the instruction was open. So the one which was recently used is open, and it is going to be stored in the instruction register. Then we have the program status word, which is supposed to give a status of a particular file. So whatever file you are working on is going to show what are the conditions of that file, and then is that file going to be interrupt enabled or disabled, and is it in a supervisor mode or a user mode. When you are dealing with computers, you know a supervisor mode is what we call an administrator mode, meaning that you have more control, you can do more activities to this file. If it is user mode, it means there is a limited number of activities you can perform on this file. When we are talking about interrupt, is those signals which are supposed to tell the system what to do. So if it is interrupt enabled, it means that the system or the operating system can be able to interrupt that file when it is being executed. So if it is enabled, that can happen. If it is disabled, it means that that file cannot be interrupted once it gets into the processor. So I hope that one is also very clear regarding the registers. So do you understand the concept of registers, where they are normally located and how they normally work? Up to there. Is that understood? Yes?
Yes.
Okay, thank you. Let us proceed. We also have condition codes and flags under control registers, and these ones are going to be bits which are set by the processor hardware as a result of operations. So when we are talking about as a result of operations, we are saying that these are supposed to tell the processor what to do. So sometimes these are bits which can be like positive result, negative result, or a 0 or an overflow. So when those bits are put there, it is going to tell the processor that this is a positive result, a negative result, depending on the operation which is being done on that particular instruction. So that is what we mean by the condition codes or flags. Then we move on to the instruction cycle. The instruction cycle is the one which is followed by the operating system or by the computer in terms of making sure that an instruction has been executed. Like when you click on file, open, and you type something, then you click on save. Those are instructions you are giving to the processor. So they will start here. Then there will be the process of fetching the next instruction, then execute that instruction, and then you finish by halting the process. So there is always the fetch cycle, which is here, and the execute cycle, which is just here. So once you're through with the execute cycle, you go to the fetch cycle. So it is as simple as that. To explain it, here is what happens. The processor will fetch the instruction from memory. And when we are talking about memory here, we can call it the main memory. Because whenever you load an application program, let us say MS Word, it will be loaded to the main memory and all its instructions. Like here, we have home, where we can talk of layout. So here are instructions you can have to show how this layout of the PowerPoint will be. There are instructions showing how to number your PowerPoint points and all of that. So all of these is in main memory. So the processor will fetch these instructions from main memory to start with. Then those instructions are fed to the program counter. That is why we were talking about the register called a program counter, whereby you are going to store, or the address of the instruction to be executed next is stored in the program counter, and then the program counter is going to be incremented after each fetch. So the first fetch maybe was file, open, new. So I click on new slide. So when I go to the next instruction, which I am performing, maybe typing something, then the program counter is going to be incremented. And then another fetch, it is incremented. And that keeps on going on and on until you are through with the operations in that file you had opened. So that is what we mean by the instruction fetch and instruction execution. Then the instruction register is supposed, like we have said, once a fetched instruction is executed, it is going to be placed in the instruction register. And there are several types of instructions. There is one we call the process memory, whereby we are talking about transferring data between the processor and the memory, meaning that after the instruction has been executed and data has been created, like you have typed something, this data needs to be transferred from the memory or from the processor to a memory somewhere. So that will be an instruction which is in the instruction register. Then we also have the data transferred, the processor I/O. It is data transferred to or from a peripheral device. Then we also have a data processing instruction, which refers to either an arithmetic or a logic operation which is performed on the data. Then we also have a control instruction, which is supposed to alter the sequence of execution. Like we are talking of control signals, this control instruction, you will find most of it is what we call an interrupt. You can interrupt an execution as it is going on. And there are several causes of interrupts that we will see later as we look at interrupt handling. But there is that register we call a control register. So here is an example of a program execution. So in the memory, we are having this 194 or 1940 is some instruction which is in memory. So when we are talking about some instruction in memory, think of a computer application program, 1940. So it will be fetched. So this instruction will be fetched and brought to the CPU register which we are calling what? An instruction register. The program counter here is storing what needs to be executed next. And then we also have an accumulator which is supposed to store what has been executed. So that is the first step, whereby you fetch this from memory and bring it to the instruction register. Then from there, this 1940, once it is in the instruction register, it is supposed now to give several activities like we have seen here. There will be either processor memory, processor input output, data processing, or control. So it is stored there to show those kinds of instructions. Then inside memory, now we have this 1940 as the next one to be executed. That is the second step. Then in the third step, now the 1940 has been put out of the CPU register because after execution it needs to be swapped out of the processor and brought to the register. In step 4, there is going to be an activity now whereby you are swapping between what is in the accumulator and what is in the CPU register, depending on what activity needs to be performed. So you're going to add 3 and 2, and that is the step 2 and step 3. This is the swapping which is taking place here. And then after that, you go to step 5, whereby we are showing that in memory there is this instruction, and it is the one in the instruction register. And after the instruction register is executed, you can see in step 6 that is being moved out of the CPU registers and brought back to the main memory after execution has been done, and depending on what was being performed, then it can be brought back. So that is just a diagram showing how contents can be moved from memory to the CPU, execution is done, and then back to the main memory. So let us look at the concept of direct memory access. When we are talking about direct memory access, what it basically means is this. There are exchanges between input-output devices and the memory, where we are talking about the main memory without going through the processor. The reason for this is that we need to relieve the processor the responsibility for that exchange, whereby there could be transfer happening, for example, between your USB device and your computer storage somewhere, and at the same time, your processor is performing other activity. Maybe you are typing a document as that copying is taking place. That is what we mean by direct memory access, whereby an input-output device can exchange data or activity with the memory without involving the processor. So the goal here is to ensure that the processor is doing other activity apart from just being responsible for the exchange. So the processor will be free to perform other activities. That is what we mean by direct memory access. It happens with modern systems because they have been enhanced, and it is possible for that to work so that processors can perform other activities. Then let us look at the concept of an interrupt. When we are talking of an interrupt, is that stoppage of the normal sequence of execution inside the processor. So why do we need to stop the normal execution inside the processor? Because as we have said, instructions come to the processor in a sequence. Activities or processes are performed in a sequence. Why do we need to stop that? So that we can improve the processing efficiency. That is one of the reasons. And also allow the processor to execute other instructions while input-output operations are taking place. Like we had said, there are these scenarios whereby a process or a process which is in execution may require some input-output activity. And when it requires some input-output activity, maybe to get some data, like when you are doing an installation, it is happening within the processor. But at some point, it requires you to click that you agree to those terms of reference. And before, since you have not clicked that button, the processing cannot continue. So before you come to click on it, that processing will be moved out of the processor so that the processor can execute other instructions as we are waiting for an input of that requirement you have been asked for. So that is another reason. Also, there can be a suspension of a process which is caused by an external process or by an external event which requires the processor to stop what it is doing so that it can perform another activity. Like for example, you could have timed your antivirus program to be updating every day at 8 o'clock in the morning. So when 8 o'clock in the morning reaches, it doesn't matter what was happening inside the processor, it will be suspended so that the updating activity can be processed. So those are some of the reasons why interrupts normally occur. So it could either be a program. So here we are looking at the types of interrupts. So we have program interrupts, either an arithmetic overflow, a division by zero, either execution of an illegal instruction. If you tried to delete any item or any operating system dependent file inside the C drive, it will not be deleted. What will happen is that it will be interrupted, or there will be an error message you will get, because that cannot be allowed. That file you are trying to delete is depended upon by the operating system for its normal operation. That is why we are talking about execution of an illegal instruction. A reference outside the user's memory space. Like for example, you had created what we call a virtual memory, and at some point that virtual memory has been used up, meaning that the hard drive space that you had allocated the virtual memory has been used for some other activity, and you are trying to reference or to make a reference to that memory space. It will not be accessed because it has already been used up and it is no longer available. When we will be looking at virtual memory, you will understand this concept. So the moment you try to access that memory location, it will not be possible, and that will cause an interrupt of the program. The other one we have talked about is the timed interrupt, like I had given the example of an antivirus update. If you had specified that it is supposed to happen at this particular time and that time reaches, or a particular program is supposed to perform a specific activity at a specific time, when that happens or when that time reaches, then that has to happen. So it doesn't matter what was happening in the processor, it will be stopped for that activity to work. If there is a need for an input-output activity, like I was giving you the example whereby you are trying to install a program and it requires you to click to confirm something, and you have not done that. So it requires some input from the user. So before that happens, that process will be stopped so that other processes can be executed as it waits for an input to be made. Hardware failure, if your keyboard has a problem, or your mouse or other critical hardware components inside your computer have a problem, then an interrupt may occur so that that problem is addressed, and once it has been addressed, then other activities can continue. So there is a program which we call an interrupt handler, and an interrupt handler is a program that determines the nature of interrupts and performs the activity which is needed regarding that interrupt. So whenever an interrupt occurs, then the interrupt handler is invoked, or it is triggered to start. And the moment it starts, control is transferred to this program, and then it will do whatever is required. Like I had given you the example of while you are installing a program. So during that time, an interrupt occurs requiring some input. You will see a pop-up message coming to you telling you, can you confirm this? Are you sure you want to delete? If you are deleting files and there is a critical file, they will ask, an interrupt will happen. So when that prompts you, it is the interrupt handler which is taking control, and it is trying to ensure that it is performing the activity as it is needed. So an interrupt handler is part of the operating system which is supposed to handle interrupts. So how does an interrupt cycle work? In the program execution cycle, where we were talking about fetching an instruction, executing an instruction, there is also the aspect of interrupt handling. So it will start the normal way. You fetch an instruction, then you execute the instruction. If interrupts have been disabled, you will go through the cycle the normal way, whereby you fetch the instruction, you execute it, and you go back to fetching the next instruction. If interrupts are enabled, then during execution, there will always be the interrupt handler checking for any interrupt. So if there is an interrupt which has occurred, then the interrupt handler takes over and the interrupt cycle comes in, whereby you will need to know, what are you expected to do? Is it an input which is required? Is it maybe an hardware problem? Is it maybe an error which has occurred? All of that is being managed by the interrupt cycle. So I hope that the diagram is clear. So this is where the interrupt cycle comes in, whereby the processor will keep on checking for interrupts. If there are no interrupts, then you fetch the next instruction for the current program. If an interrupt is pending, then you have to suspend the execution of the current program and then execute the interrupt handler. And here is an example. So we had this user program which is performing some activity. So it starts, and if there are no interrupts at this first instance, we have no interrupt. So during this first instance, the user program will come in here if there is some activity which is taking place, a writing activity, which will require the input of maybe an input-output program. So here it will require some writing activity to take place. Then it will continue with the writing activity and finish the execution of that program, and it ends. So nothing much, nothing complicated. We are just expanding here to show that during the writing process, there is the input-output module which has to be executed or has to be brought aboard, and then the input-output command is executed. Like if we were trying to run a program, an installation program, then there will be some writing activity in the C drive, and it will require you to click to accept the terms and conditions, and then the input-output command is executed and the activity ends. So it is as straight as that. But look at the second scenario, whereby there are interrupts. So the moment you are waiting for some interrupt to take place, here the star here is showing some interrupt which has taken place. So at this star, the interrupt handler will take over. So during the execution here, there may be required some kind of input-output which is needed. So as it is being required, or as it is being waited for, that is where we have 2A, step 2A and step 2B. Then during 2A, an interrupt occurred which required some input-output to be done. like maybe accepting the terms and conditions. So before you do that, the interrupt handler takes over, and it gives up the processor to another process to continue until you are through with this interrupt process. Then step 2B continues. If another interrupt occurs here, then the interrupt handler again takes place and continues until you are through with your process. So that is what it means by the interrupt. This could be a short input-output wait, and this is a long input-output wait, where the interrupt handler is taking over. So that is what it means by that diagram. When there are multiple interrupts, then disable interrupts while an interrupt is being processed. So if there are several interrupts, like here, it is a user program which is in execution, and then interrupt handler X takes over. So when there is another interrupt, what happens is that it cannot go back to here. So we are talking about the sequential interrupt processing. You will have to finish the interrupt X before you continue to interrupt Y. But here we have the interrupt X, which has come here, but it also requires some input-output, for example. So interrupt Y takes over within the interrupt X. So there are those two types of interrupts, whereby you can have an interrupt in sequence or an interrupt within another interrupt. So that is what it means to have multiple interrupts. So multiple interrupts which have sequential ordering is whereby we are going to disable interrupts so that the processor can finish the task. This is what we are talking about. Finish this one before you take the next one. Or we are also having the sequential order whereby interrupts will remain pending until the processor has enabled interrupts again. And after the interrupt handler routine completes, the processor checks for any additional interrupts. When we come to multiple interrupt priorities, it is the case whereby an interrupt comes whereby whatever is being needed has a higher priority than what is inside the processor. So even if the interrupt which was taking place is still continuing, there needs to have a higher priority, then that interrupt will be interrupted and the higher priority interrupt takes over. This is the example here we are talking about. Higher priority interrupts cause lower priority interrupts to wait. That was the second example we had given here, whereby this is a higher priority interrupt than this one. So even if this one was taking place, it will be stopped by the higher priority interrupt. That is what we are talking about here. And an example here is given whereby an input from a communication line which needs to be absorbed quickly to make room for more input needs to be done. Then whatever was interrupted first will be stopped so that this one can take over. Then we come to multi-programming. And before we continue there, that is where I need to stop for today in regard to components of the computer before we go on to the concept of multi-programming. Any question up to there?